Good afternoon. In my last lecture, I was speaking about multiphase reactors and I was discussing the trickle bed reactor. So, today also I will continue that some design aspects and fundamentals of the trickle bed reactor and then for fluidized bed reactor. So, I was talking about a gas, liquid and solid. So, you can see here there is a gas bubble, right, and this can be a case of slurry bubble column reactor also, and here I am talking just a trickle bed reactor, but it is for any gas, liquid and solid reaction this kind of system, whether it is slurry bubble column reactor or trickle bed reactor or even in a fluidized bed reactor, right. The scene may little bit different, but the in total there will be a kind of resistances offered, right. So, this is a gas bubble and then there is a concentration here at the interface and you have a bulk of liquid. So, this section is showing the bulk of liquid. So, from here there is a mass transfer from the external surface of the bubble to the center or the main body of the liquid, right. So, in between there can be a gas film resistance as I discussed last time and the liquid film resistance. So, KAL, right, in the liquid side and same thing KAG is the mass transfer coefficient for the gas side. And from this main body of the liquid there is a transport from the gas A from the liquid, that is main body of the liquid, to the external surface of the solid, which will again be governed by the concentration difference, that is here of this concentration of gas A and concentration of gas A at the surface, which is again a mass transport step. Once this happens, then the fourth and fifth step, these are related to the diffusion into the pore of a catalyst and followed by chemical reaction. So, in chemical reaction again we will have the surface reaction. So, first adsorption of gas, then surface reaction and then desorption of the product. So, that is inside the surface of a catalyst. So, if the catalyst is porous. So, this is one resistance in terms of the mass transfer and this interfacial area which is depending on the size of the solid particle, right. What is the surface area of this catalyst per unit mass of the catalyst or per unit volume of the catalyst. When you look at here the mass transport, it will depend on the interfacial film, that is the liquid film which has formed. So, one side it is gas, other side is a liquid and this is a film and thickness of that film will be important, and how to minimize that thickness is nothing but a kind of reduction in these resistances as I discussed in my last lecture. We also discussed this picture. So, I said that this is the main body of the gas where the pressure is PAG, right, and then it reached to. So, this is a kind of gas film and it reached to the surface of the liquid, right, and this has some kind of resistance. So, KAG or Kg times whatever the concentration here and Ca minus Cai, right, and same thing here the equilibrium. So, Cai and Pai can be related, right, by Henry law constant. So, Pai is equal to Ha times Cai something, right, and then this from here it is coming to the main body of the liquid. So, gas diffuse into the main body of the liquid or there is a mass transfer. So, again it will depend on the concentration Cai and concentration in the main body which is written here Cal. So, this is the main body of the liquid. So, Kal times interfacial area times Cai minus Cal. When it reaches to the main body of the liquid, so here the concentration is uniform and then you have a diffusion from main body to the external surface of the solid, because this is surrounded, this catalyst particle is surrounded by a film of the liquid, right, and this mass transport will depend on this mass transfer coefficient which is film coefficient about the catalyst particle, and also it will depend the surface area of the solid per unit mass or per unit volume of the catalyst, right. So, that is again the transport or mass transfer and then followed by the diffusion into the pores, which will depend on the effective diffusion coefficient of A and effective diffusion coefficient of B, right. So, depending upon the type of solid, it may be bulk diffusion, Knudsen diffusion. So, these steps may also control the overall rate of reaction. So, the concentration profile you can see CAS from surface of the solid, it drops like this, and that will depend on the effectiveness factor, that is the pellet effectiveness factor. Cb is again the concentration of B, which will depend on the diffusion coefficients, right, on the property of the liquid and the pore characteristic. So, that has been discussed earlier. So, just I would like to recall the steps, right, which is for the heterogeneous gas solid reactions we have already discussed. We derive the rate equations, right, and we assume certain steps as the rate controlling. Thus, similar approach is used in all the reactors, right, whether the only thing that the mass transfer resistance, gas side, liquid side. So, the coefficients are to be calculated from the hydrodynamic study or from the correlations. So, gas A reacts with liquid which is B and transform into a product, right. This is the simple stoichiometric reaction which we have assumed here. So, the gaseous reactant A reacts with a B which is not transferring into the gas side. So, it is a non-volatile kind of liquid under the condition of the reaction, right. And already the liquid is inside the pore of the catalyst, that is the catalyst pores are already saturated with the liquid. So, if you look at the mechanism in these kind of reactions in a multi-phase reaction system. So, first step which I discussed is the mass transfer of component A from the bulk gas to the gas liquid interface. So, this is sketch wise if I just show you again. So, this is a solid catalyst where you have a film of the liquid like this, a uniform size, right, and then you have a bulk liquid. So, this is your bulk liquid and then you have a film of the liquid. So, I will say a kind of interface here, and so this is your liquid film. So, liquid film here, and then there is a film of the gas. So, gas comes from here to here like this, right, and then this is a bulk gas. So, this is a bulk gas this side, right. So, gas. So, this is a gas film, this is your liquid film, and from here it reaches to the bulk liquid. So, this is the same concentration throughout, but when it reaches to this surface. So, again there is surrounded, the solid particles are surrounded by the liquid film. So, there will be a gradient. So, again there is a transport, and then in the porous structure you have diffusion and chemical reaction here. So, inside this, so diffusion and chemical reaction. Okay. So, this is what the first step, the mass transfer which is a gaseous species from bulk gas to the gas liquid interface. So, from main body of the gas it will come to the surface of the bulk, that is the liquid film, that is the it is a film of the liquid, one side is the gas, other side is the liquid. So, that is the first step. So, it will depend on the mass transfer coefficient of this gaseous species, this is the mass transfer coefficient, the area of the interface, right. So, in the gas liquid reaction, as you know, the interfacial area is very important, right. Same thing here, because it is a kind of the solubility of the gas into the liquid, right. So, it will depend governed by the Henry law and other experimental conditions, right. So, it is basically the interfacial area of the film, right. So, times the pressure, that is P A or C A, right. So, partial pressure of gas A and minus the partial pressure of gas A at the interface. So, with these 2 points which you are talking here. So, P A and P A I. So, this is the first step which is K A G times A I times P A minus P A I, which is the transfer or rate of reaction, which can be written in terms of minus 1 upon V dNA by dt, because all the time we are writing our minus R A is equal to minus 1 upon V dNA by dt, right. So, this is per unit volume of the liquid, bulk liquid. So, the choice can be based on the volume of the liquid, which is if it is slurry bubble column reactor, right. It can be defined per unit mass of the catalyst like in a trickle bed reactor or volume of the catalyst. And this is what the moles transported, right. And if I write it, so this same thing is your whatever you write here K A G times the interfacial area, right. It may be per unit volume of the same unit, right, liquid times your pressure difference P A in the bulk minus P A I which is at the interface, right. And because steady state all these rates are equal. So, whatever the molecules transports from here to here, the same molecule will come to this film and same will go here in this, diffuse through that and react chemically. So, this is your rate of reaction. The only thing that depending upon the resistances offered by each, so you have summation of all these resistances because these are acting in series, right. So, one needs to minimize these resistances depending upon the severity or depending upon the system, that is trickle bed reactor system or slurry bubble column reactor. So, you have to select a system whether your gas film resistance is very high or liquid film resistance is very high or the diffusion and chemical reaction in a pore of a catalyst is very high, right. If the diffusion and chemical reaction controls the rate, obviously you would like to have smaller particles, right. If your liquid side resistance or gas side resistance is dominating, then obviously one would like to have a bubble column reactor or a slurry bubble column reactor, right, large volume of liquid or large interfacial area. So, a good kind of sparger design where you should have small gas bubbles diffused through that, right. So, depending upon the solubility of the gas. So, all these design will be important, a kind of sparger, good kind of sparger, good kind of agitating system, your catalyst particle size. So, everything is important because you need to minimize all these resistances. So, this is first step. In the second step again as I said from here to here. So, second step is mass transfer of gas A from the interface gas liquid interface to the bulk liquid, right. So, you have a gas film, you have a liquid film. So, liquid from here it reaches to the bulk liquid. So, that is the second step. So, K A L which is the mass transfer coefficient in that liquid film, A I is the again interfacial area, same interfacial area, C A I is now concentration of gas A at the interface, which can be related to P A I by P A I is equal to H A times C A I. So, one can write the Henry law P A I is equal to H Henry law constant times C A I, right. So, that will decide the depending upon the solubility of the gas, the concentration of gas in the liquid will be different, right, and you have to look at accordingly a good kind of design or selection of a good kind of contacting pattern. So, once this happens, the gas reaches to this bulk, then there is a transfer of A. So, mainly it is B is already there. So, I am talking the transfer of A from the bulk liquid to the external surface of the solid. So, this is a solid covered by a film of liquid. So, there is a transport. So, this is the third step and this will depend what is the mass transfer, it will depend on the size of the solid, right. So, simply this K C a mass transfer coefficient which is here to the at the surface of the solid, A C is now based on surface area of the catalyst per unit volume of the catalyst or surface area of the catalyst per unit mass of the catalyst. So, either unit can be used and accordingly the total rate can be calculated. So, here if you define based on this, it is per unit volume of the liquid. So, C A I which is again here the concentration at the interface minus C A S, where C A S is the concentration of A at the surface of the solid. So, C A S is here at this point the concentration is C A S, right. So, if the solid is non-porous, this will react here only, right, but if it is a porous material. So, now this will diffuse from here to internal surface. So, again there will be a kind of concentration gradient. So, this is what the step. I already said that B we are assuming is already there, if it is not there then B will also diffuse, right. So, intra-particle diffusion of reactant species, that is mainly here A, through the catalyst pore to the active site. So, again one needs to find out the pellet effectiveness factor. So, pellet effectiveness factor will be based on whatever the Thiele modulus, right. Thiele modulus will depend on the size of the catalyst particle, right. So, all these factors what we have learned before, these will be utilized here also, because your effectiveness factor is very important and we need to control that. That is, we need to basically maximize that, or approach should towards the 1 if there are no diffusion resistance. So, try to minimize that, right. Adsorption of both one, right, both or one reactant on the surface of the catalyst. So, these 3 steps, your adsorption, surface reaction and desorption are related to the kinetic step. So, that is basically once the reactant reach to the internal surface of a pore, now it will be a chemical reaction at the surface. So, chemical reaction at the surface means we have already discussed that the reactant species, suppose A gas, it adsorbs on the active side and makes something like AX, which is your adsorption step, right. And same thing, that your AX, which is already adsorbed, now will react with liquid B and transform it into a product. So, that is a kind of surface reaction. So, either A is adsorbing or B is also adsorbing. So, both possibilities are there. So, if B is also adsorbing, you need to write B plus X is equal to B X, like this, right. A plus B, these are your reactant, right, and then product is forming. So, the product is forming, then you have just like something like, if I say R is the product, and then it may be adsorbed species and plus 1 vacant site, right, and then this R X will desorb and will give you a product R and another vacant site, right. So, this is what we discussed before in the kinetics, right, of the catalytic reaction, right, heterogeneous catalytic. So, these steps will take place and finally, you have a product. So, all these one diffusion and the chemical reaction, they can be clubbed together and one can write this diffusion effect in terms of effectiveness factor. So, eta is your palette effectiveness factor. So, what is written here? If I write this, the overall rate because of diffusion and chemical reaction is equal to whatever the eta times the rate for the main reaction, because this is contributing the diffusion. So, eta times I will write it R intrinsic, right, that is in the absence of diffusion resistance, and that R intrinsic can be determined from Langmuir model what we have written here, or it can be determined based on the your overall power law model also. So, here if you assume that it is simply a eta times k times C A times C B, suppose first order with respect to A and first order with respect to B, and so this is your rate of reaction per unit volume of the catalyst or per unit mass of the solid. If you write it per unit mass of the solid, then it should be multiplied by fraction of the solid present in this bed, right. So, that is the additional term which you see here is only when we are calculating the rate of reaction, right, because it is based on the mass of the catalyst or volume. So, fraction of the catalyst or solid in the bed, or one can write in terms of the mass or concentration of the catalyst, mass per unit volume of the catalyst, especially when you have a bubble column reactor, right. So, slurry bubble column reactor where catalyst concentration is also important, right. So, the mass of the catalyst will come here because we are calculating the total rate of reaction or total moles which have been transported, right. So, this is per unit volume choice is yours, that will decide based on the unit of the small k which is written here. So, per unit volume or per unit mass fraction of the catalyst, right. C A and C B, C A is the concentration of A. If I say that C B is already present, so I can write this eta times some constant k dash times C A, and most of the time in trickle bed reactor we assume that it is a kind of first order kinetics, right. So, whatever the difference that can be taken care by the unit of k dash or in the value of k dash. So, if you look at all these steps, as I said here, right, at a steady state all these rates are equal, right, because whatever the moles which have been transported like this from the surface, right, like this, the same moles are transporting and diffusing and reacting chemically. So, it means this value K A G P A minus P A I will also be equal to this value, right. Only just you have to take care of the units, right, per unit volume. So, multiply by the volume of liquid, per unit mass, so multiplied by the mass of the catalyst, right. So, the unit consistency needs to be checked, and then all these rates are equal in this reaction, right. And if this is the case, then very easily you can derive the expression which is written here in this form, right. So, what you have to do simply, because these are indicating the all these steps are in series. So, K A G times A I times P A minus P A I will be equal to K A L, which I defined earlier, times C A minus C A I minus C A L, right. So, that is what the step I can write here again for you. So, in that form, so K A G, which is the mass transfer coefficient on the gas side, times A I, which is interfacial area, times P A minus P A I, this is the first step, will be equal to K A L times A I, again interfacial area, times C A I minus C A L, which is the transfer from interface to the liquid phase, right. So, will also be equal to, because these steps are in series. So, whatever the moles transferred from because of this, these mole will go to the liquid and they will diffuse to the external surface of the solid. So, whatever K A small a at the surface of the solid times small surface area of the catalyst per unit volume or mass times C A L minus C A S transport to the surface of the solid, and then there is a diffusion and chemical reaction. So, K dash times eta times C A S, or if you need you can write this fraction of the solid. So, all these rates are equal at steady state. Right. So, one can simplify this because one can eliminate these intermediates. So, this P A I, all these your P A I, C A I, C A L and C A S are to be eliminated from your overall rate equation. So, basic idea is that this is equal to this, this is equal to this, this is equal to this. So, you just make the equation different set of equations and then eliminate. So, one can very easily write it like this. So, P A minus P A I from the first, right, expression, which is your minus R A, if I write minus R A in any convenient unit, right. The unit per unit volume or per unit mass can be written like this, right. So, what I mean to say, my P A minus P A I is simply your minus R A, which is the volume N A in one way, total moles reacted, if I calculate on any convenient unit. So, multiply by the volume or whatever and divide by, you will have here K A G A times A I, something like this, right. Similarly, in the second case you will have C A I minus C A L, right. In third case you have C A L minus C A S, and in fourth case you have C A S is equal to again minus R divided by your K dash times eta times F S, something like this, right. So, you can write this step, you can write this step yourself. So, what I mean to say, if I C A I and P A I are related by Henry law. So, I can write this either P A I in terms of C A, or I can write this C A I in terms of P A, right, and then divide it. So, your Henry law constant will also come in the denominator, right, in all case. So, basic idea is that I can, if I add all these, so these term will be cancelled, right. So, add 1, 2, 3, 4, all 4 equations, right. So, you have what left? P A here. So, P A is equal to this R is common, right, and the term in the rest of the term will go in the bracket, which is representing nothing but a combined resistance, right. So, one can very easily write the P A is equal to H A, that is at the interface. So, H P A I H A times C A I. So, your C A I is simply can be rewritten in the form of any convenient unit of Henry law constant, and if you do that and add this. So, here the rate of reaction per unit volume is mentioned for A, right, R A triple dash, right, which is simply now your PAG, which is your PA gas phase concentration, a known value, right, at the inlet the gas phase concentration, total pressure into mole fraction of that gas. So, this is known to you, and the rest of the terms are representing, this is the resistance in the gas film, this is the resistance in the liquid film, this is a kind of resistance from mass transfer from the bulk liquid to the external surface of the solid, and this is the resistance which is offered because of diffusion and chemical reaction, right. So, what do you see from this? If you add all these, you have this expression which is your minus R times 1 upon K A G A I, here it is again 1 upon K A L A I times the Henry law. So, which has gone to the numerator side, right. So, you can very easily write this expression, and then you have the expression for the overall rate. So, now which step is dominating will depend whether your mass transfer coefficient is very high, liquid side mass transfer coefficient is very high, surface of the solid, right, that is mass transfer coefficient at the surface of the solid is very high, or this chemical reaction constant is very high. So, it means by having a suitable temperature, right, by selecting a proper catalyst size, right, these two can be controlled. So, you have a good kind of catalyst particle size, right, diffusion is one, porosity of the particle, right, and kinetics is there. So, temperature of the particle. So, resistances can be controlled. Same thing on this side also, if you look at KAG and KAL, they depend again of the size of the bubble, gas bubble, right, and a kind of stirrer design. So, basically it is interfacial area per unit volume. So, small size bubbles you need to have in your reactor if you have a bubble column reactor, right. So, that is the mass transfer coefficient. This will be a function based and can be calculated depending upon the hydrodynamic study. So, one can do the hydrodynamic study and one can find out the mass transfer coefficient, right, and accordingly again the interfacial film thickness, right, which is, as I said, just simple example, smaller the bubble. So, if you have bubble column reactor, you design a good kind of sparger. Same thing for the trickle bed reactor, you need to design a good kind of distributor, right. So, that is KAG, KAL, which are related to the empirical formulas, right, or can be calculated depending upon the hydrodynamics, and one can control these, or one can maximize the coefficient or minimize the resistance, because these are nothing but the resistances offered by each step, and this step is your overall resistance. So, here this eta is represented by this, right. So, effectiveness factor for the first order reaction with respect to a rate constant, which is taken a pseudo first order rate, right. So, rate constant times the concentration of B, we have assumed that B is in excess, right, and HA is related to your Henry law constant, as I said. So, PA is equal to HA times CA, and again depending upon the solubility of the gas. So, as I said, if the gas is highly soluble, its Henry law constant is low. If gas is sparingly soluble, that is very difficult to dissolve in the liquid, then its Henry law constant will be very high, right. So, one can again design the system depending upon the solubility of the gas, or give the high pressure to, because at high pressure your solubility will be high. And there is always a relationship between the rates. So, I told you that R A upon A is equal to R B upon B. So, it will depend on the stoichiometric coefficient. So, one can very easily write that if this much moles of A reacted, how many moles of B will react. So, one can very easily write down the expression for that also, right. So, just one is sufficient, because in design equation generally we write the rate of reaction based on limiting component, and one can very easily write down the reactor design equation, because this is the rate equation. And when you have a trickle bed reactor, it will behave like a plug flow reactor. If you have a slurry bubble column reactor, you can resemble it to like a CSTR. So, you can have the overall volume of the reactor required or mass of the catalyst required for a given conversion. So, most of these liquid phase reactions, right, hydrogenation of the vegetable oils, right, and they are generally carried out in the bubble column reactor, and if there is a catalyst in that, so you have a slurry bubble column reactor. So, you have a concentration of catalyst which is important there, right, that is the how much mass which you call catalyst loading there, mass of the catalyst per unit volume of the solution, basically volume of the reactor, right. So, that is very important. And second thing is that the size of this catalyst particle, that is again important, because these are offering a kind of resistance. So, smaller particle size will be preferred, because your effectiveness factor will be higher when your particles are smaller in size. This is one thing, right. Same thing, if the gas which is being bubbled, you should have a small bubble size, right, and then you need to have a good kind of sparger there, right. So, same expression is written here in terms of that, but I have already talked, if you write it in terms of per unit mass of the catalyst. So, only the overall rate constant. So, sometimes this all term which is written together here, we can write it in terms of the, because 1 upon this plus this plus this plus this is representing the overall rate constant for the reaction. So, I can write it like this, minus R A triple dash is equal to capital K some overall rate constant times whatever P A G, a kind of overall first order rate, right, where this is contributing to all resistance. So, if this is negligible, this is negligible, this is negligible, you are just like a kinetic rate, right. So, in terms of the concentrations. So, when you do the reactor modeling, so first thing is that you have to look at the hydrodynamics of the reactor in the case of multiphase reactor, very important, right, and from that you have to find out the resistance, then you identify the overall rate of reaction, and once the rate of reaction is known, then one can go for the sizing a reactor, right. So, this is what is done in the trickle bed reactor also, right. So, a kinetic model for a trickle bed reactor is generally assumed a first order with respect to both reactors. So, generally liquid is already there in the bed. So, liquid is in excess. So, we make it a pseudo first order rate, right. So, if the reactor is ideal and the catalyst is completely wetted. So, most of the time your wetting efficiency here it comes out to be 1 for the complete wetted surface, right. The conversion in a first order reaction, as usual you know that F A naught d x A is equal to minus R A dash d W. So, all of you know this design equation. So, a reactor design equation for a plug flow reactor. So, F A naught if I write in terms of molar feed rate times d x A for a differential element is equal to minus R A, either you write in terms of per unit mass or per unit volume. So, here it is written per unit mass times d W, where d W is the mass of the catalyst in the bed, and the mass of the catalyst in the bed can be written in terms of the density of the catalyst and times the volume of the catalyst, right. So, R A dash can be written in terms of R A triple dash into d V also, right. So, in the here we just reported it in terms of R A triple dash, right, but always you can write the expression as I said just by relating it with the density of the catalyst. So, this is the same expression which is written here, where F A naught is simply your C A naught into V naught, right. So, C N F A naught is molar feed rate. So, F A naught is related to your concentration of A times the volumetric feed rate, right. So, this is your volumetric feed rate. So, one can write in that form also. So, and this minus R A dash which I was talking in terms of mass of the catalyst. So, your K will convert to something like a K dash, that is based on the mass unit, and if there is a diffusion limitation, right. So, intrinsic rate which is K times C A. So, C A will be nothing but C A naught 1 minus x, right. So, basically this thing which is written here C naught is your C A naught, concentration of A at the inlet, right, and this is here it is written in terms of the volumetric feed rate, right. So, which is same expression here, and K times rate constant times the effectiveness factor times the concentration which is related to at any point, right. So, this is C A naught 1 minus x A. So, x A is the fractional conversion. So, this data is simply in terms of the intrinsic kinetic. So, since there may be a diffusion limitation, so we have introduced a eta into effectiveness factor, right, which is for isothermal case always less than 1, right. So, this is the effectiveness factor in the pellet. So, this is again a simple first order rate, right. So, one can very easily integrate this by writing d x upon 1 minus x, and this side it is 0 to W dW, total mass of the catalyst required or volume of the catalyst required in the reactor. So, this is simply dx divided by 1 minus x and integrated, right, from 0 to x, and this side it is 0 to W dW, because all other terms are constant at one temperature. So, if you integrate this dx upon 1 minus x, it will be simply log of 1 over 1 minus x, right. So, this is the integration of dx. So, whatever you have dx divided by 1 minus x. So, I will write it dx over 1 minus x, right, something like this, and integrated over that. So, something like this. So, here if I write it, so dx over 1 minus x is this, and limit is 0 to x. This is the term which is here, and integration of this is here, right, which is simply ln of 1 over 1 minus x, and this rest of the terms have been taken to the other side. So, you have k, you have eta, integration 0 to w is your w, right, divide by f. So, C naught gets cancelled. So, these two terms which is here written f a naught is C naught into V naught, but here it is written only in terms of the volumetric flow rate. So, this gets cancelled here, right. So, this equation C naught and C naught both are common. So, this gets cancelled here, right. So, finally, you have k eta and this is w now divide by f, right, and one can write it because this w is nothing but the bulk density of the catalyst into volume of reactor, right. So, what is the actual size of the reactor will depend on the bed porosity, void bed fraction. When I write it bulk density, it is nothing but the actual density of the catalyst plus whatever the void fraction they are. So, basically in terms of the volume, if I write the reactor, so volume of reactor is not only the volume of catalyst plus the total void volume of the bed volume in terms of the void fraction of the bed, right. So, that will increase the size of the reactor. So, this is actually the same expression what you have seen here, and one can write it in terms of the mass feed rate or the volumetric feed rate also. So, this same expression have been reported or has been reported here in terms of dFA by dW, which is equal to your RA dash based on per unit mass of the catalyst, right, and this we have defined in terms of the overall rate constant for the reaction times the concentration of A in the gas phase, bulk concentration, whether you write in terms of partial pressure or concentration, no problem, only this unit will change accordingly, right. So, we have written already in terms of RB relationship. So, one can write in this form also, which is not required here, right. So, because this is simple design which we have already done earlier, F A naught and F B naught are interrelated, simply minus R A and minus R B are interrelated, right, and that has been done here in this form when you write it in form of B also, right. So, because you know what is dFA and what is dFB, right, based on the stoichiometry. So, Fa is Fa naught 1 minus Xa, right, and if you write it in terms of the B, so if they are taken in the extra stoichiometry ratio, equal number of moles of B will react. So, one can write in terms of that also, right. So, either way, but generally it is advisable to use the limiting component. If no limiting component, then one component can be written with the stoichiometry 1 and then one can solve the expression. So, the expression has been shown what we have discussed earlier. So, I am not going in this form. So, sometimes we call it liquid hourly space velocity. So, liquid hourly space velocity is related to something, the volume of the catalyst in the bed, right, that is the and the volumetric feed rate, right. So, just like your space time which we have defined, right, or weight hourly space time, sometimes W by F A naught as I discussed earlier. So, this term which is here W by F A naught, so that you define weight hourly space time, right. So, I can write it W H S T, but most of the time in the case of trickle bed reactor it is defined based on the LHSV, that is the feed which is at the entering condition is the liquid, right, or sometime we can define gas hourly space velocity also, right. So, liquid hourly space velocity means the reverse of this, right, and only thing that now you are defining in terms of the volumetric feed rate of the liquid. So, volumetric feed rate of the liquid, if I write it by V naught divide by the volume of the reactor, which is or mass of the catalyst in the bed, right. So, here it is defined in terms of the volumetric feed rate divided by the volume of catalyst. Right. Effectiveness factor, because your equation or expression is has the effectiveness factor. So, that is also equally important when you want to look at the design aspect. So, theoretically we would like to have effectiveness factor 1, right. So, no diffusion limitation at the surface of the catalyst, right, or internal. When we look at the pore diffusion resistance, we would like to have maximum concentration, because your effectiveness factor will decrease the concentration to some value like this if the eta is very high, eta, right, if you look at here. So, your or I will say that rather writing eta, I will write it Ca by Cas, right, and this is your distance, right, from the 0, if I say r, and here it is your center, right, 0. So, to be something like this, which we have discussed earlier in our pellet, that is Ca by Cas, the concentration at the surface, right, of the solid. So, your Cas is here and Ca is talking at the center of the pellet. So, when you have, if I write it in the form of dimensionless form, so I can write here r is equal to capital R, boundary condition if you write. So, at r is equal to capital R, your Ca is equal to Cas, right. So, your Ca by Cas will be 1, Ca by Cas is equal to 1 at, if I define the dimensionless concentration, r by r, right, that is r by capital R as 1, right. So, this is my point 1, right. So, here you have the concentration 1, and then r is equal to, suppose if you have the center. So, there can be a symmetry, right. So, dCA by dr is 0 here at the center, or basically you will have a kind of gradient because of symmetry, right. So, your concentration profile will go like this, right, and reach, it will approach to 0 or a minimum at this point, right. So, this is something like your where r is equal to 0, center of the pellet, and then you have symmetry on both sides, right. So, this is important to find the concentration profile, right, of the reactant material or limiting component, that is gas A, right, in the pore of a catalyst. So, theoretically what we want? Theoretically we want it something like that, not too much drop, right. So, otherwise suppose the diffusion resistance is very high, then it may drop like this, just at a half of the center or half of the distance, your the concentration becomes 0. So, rest of the surface of the catalyst is wasted. So, we do not need that. So, this is very important. So, effectiveness factor or design of a good catalyst becomes very important in the case of trickle bed reactor also. So, whether you look at the mass transfer resistance, you need to look at a definite size and shape of the catalyst, because you would like to have large interfacial area and the large surface area of the catalyst per unit volume, external surface area, right, and that will depend on the shape of the particle, size of the particle. So, that is again important for the design of a catalyst particle, right. So, simultaneously for internal diffusion, you need to look at this factor, effectiveness factor. We have already discussed this, right. So, this effectiveness factor in general, if I say eta is, when you have a diffusion limitation, eta is going something like this, 1 upon phi Thiele modulus, right. This is phi Thiele modulus. If this is the case, for different cases you have seen, right. So, phi is related to your size. So, first thing is that take a smaller particle, if this is very large, right, size of the particle, and also simultaneously it depends on the rate constant, and there are several, actually when you write it based on the volume, it is simply k by d, right, for a first order reaction, right. If you write it based on surface area, based on mass, so you have a different expression in that form, otherwise it is same, right. So, whatever this is a surface rate constant here, right, and this is your density of the catalyst. So, K s times rho, right, T e, right, or when you write it, because you know this relationship. So, that choice is yours. So, R A dash into mass of the catalyst is equal to R A double dash into surface area of the catalyst is equal to R A triple dash into volume of the catalyst, right. So, one can write the relationship which is related to, so it means K dash so the mass transfer, the rate of reaction based on the mass of the catalyst times W is equal to K double dash. So, rate of reaction which is based on surface area. So, Ks also you write times the surface area of the catalyst, right. So, sometimes the surface area of the catalyst if you write BET which is meter square per gram. So, multiply by the mass of the catalyst also here, and that is equal to K triple dash which is based on the volumetric rate constant times the volume. So, one can very easily write these relations. So, K double dash S is simply your K dash times W divided by S, right. That is the mass of the catalyst divided by the surface area of the catalyst, or if you write K triple dash and V. So, K triple dash is equal to K double dash times S divided by V, right. So, generally this S if you write based on surface area meter square per gram of the catalyst, right. So, here it will be per unit volume of the catalyst, right. So, this volume will be in the denominator. So, this becomes K times S times rho BET surface area multiplied by the density of the catalyst. So, likewise this is what the term written here. So, K double dash which is surface area times the rate constant based on surface area times the density of the catalyst. So, it is basically the S which is written is the surface area of the catalyst, and this is density of the catalyst basically, right, divided by D. So, one can write it, or one can write this phi directly R under root of K by D, where this K is based on volumetric rate constant. So, this is very simple to remember. So, this is based on volumetric rate constant, and one can very easily convert this K from this relation, right. So, this is surface area of the catalyst, this is volume of the catalyst, and this is mass of the catalyst. So, one can very easily write. So, if I write mass per unit volume of catalyst, so K triple dash can be written K dash times rho, right, density of the catalyst. So, one can write it K dash times rho also, or when you write it in terms of Ks. So, K triple dash is Ks times S divided by V, right. So, if I write S in terms of BET surface area, then S which is meter square per gram, and this is volume. So, that becomes density, right. So, surface area and the, so surface area here given in meter square per gram, and this is the density. So, the terms should be dimensionless, that is important, that consistency of the unit should be checked in order to make this phi a dimensionless unit. D is the diffusion coefficient, all of you know. R is the size of the pellet, right. So, one can know that for a spherical pellet, this is the definition, cylindrical pellet L is R by 2, right, surface to volume ratio basically, and slab it is the characteristic length, that is width of that slab, right. So, these kind of expressions have been used, right, and then reactor design models for defining what I have done earlier, that steady state all these rates are equal, but there can be the axial dispersion terms, there can be radial dispersion terms. So, depending upon the non ideality parameters which can be studied based on the hydrodynamic study or RTD studies, right. So, by using the residence time distribution studies in a multiphase reactor, one can find out the value of non ideal parameter, that is axial dispersion coefficient, right, in terms of the Piclet number, in terms of dispersion number, and these factors can be introduced when you write the moles in, right, moles in because of convection, moles in because of the dispersion term, right. So, and there can be different kind of systems, open, open, close, close, these I am not going to discuss in this, but one can write the boundary conditions also accordingly. So, a simple mass balance, as I discussed now, that whether you write the mass transfer or a chemical reaction at steady state, all these rates are equal. So, whatever you need, the input minus output minus disappearance because of chemical reaction in a reactor at steady state is 0. That is very standard design equation, whether it is a fixed bed or multiple, your design equation will based on the mass balance and the energy balance, right. So, same thing, energy balance means energy input minus output minus disappearance because of chemical reaction, and that is again at steady state if you talk is 0, right. So, these steps have been discussed. So, something where first thing I told that KCAC at the interface, if I calculate times Cg concentration in the gas phase minus concentration at the surface of the solid. So, this is just a simple gas solid reactor, right, just a simple packed bed reactor where you have a gas, you have a solid, right, and gas is diffusing through that. So, Cg is the concentration at the gas phase minus C s is the concentration at the surface of the solid, right. And at any point, if I just talk a height of the reactor at any differential section, so that will be the effectiveness factor, pellet effectiveness factor times the rate, net rate, right. And this net rate we got from the our expression, that is what I wrote at steady state, all these rates are equal. So, eta times basically this is your intrinsic rate here measured at the surface condition, right. So, if you have a equation for reactor design, so you know that now the input minus output minus disappearance because of chemical reaction is equal to 0. So, your input which you are writing here is just because of the convective flow, right. So, F A Z, which I have already discussed earlier. So, F A at Z minus the same thing F A at Z plus delta Z, right. So, input minus output minus disappearance because of chemical reaction R A dash in d W is equal to 0. All of you know this thing, right. So, now what is F A Z? It is because of the convective term and because of the dispersive term. So, I told you earlier that it is simply U times C A, right, times the area of cross section of the bed. So, this is at Z if I do not have any dispersion term, right. So, there is no dispersion term here. So, one can very easily, if there is a dispersion term, I will write plus minus or minus d d C A by d Z. This is your axial dispersion term which has been evaluated from the RTD study. So, this case says that this is 0, right. Then you have only this term. So, this thing at Z and same thing evaluated at Z plus delta Z, right. Area of cross section is constant. So, one can have the expression which is related here, because this is given in terms of this W, which is mass of the catalyst, one can write in terms of the density of the catalyst and volume of the reactor. So, in that case you have minus U g d C g by d Z, right. This is the convective term because of that, right, convective, and this is your disappearance which has been written in terms of this, because this whole term is equal to this mass transfer, the same term, right. If there is the mass transfer is the controlling, then rate is given by that, right. So, K is C A C times C g minus C s at the surface. So, it is something like a non-porous catalyst pellet also, where you have a concentration in the gas phase, concentration at the surface. So, we can do it for the monoliths also or any non-porous solid catalyst, right. So, expression will come like this. And if you have a dispersion model, which I was talking just here, so you will have additional term which is because of dispersion, right. So, d d C A by d Z at Z and same thing will be evaluated at Z plus delta Z. So, ultimately you get d G, which is the dispersion coefficient, times d 2 C A by d Z square, right. So, this is d Z square here and other terms are similar, right, u g d Z by d Z, and this is the third term which is the reaction term. One can write either this equation or one can write eta times R also, both terms are same, because steady state both these rates are equal, right. So, this is what here, and the energy balance is also required. So, I told you that heat input, it can be because of the convective transport. So, you need a kind of term mCp dt, right. It can be because of conduction also, then you need lambda dt by dz, what we write here similar to that, right. So, you have the equation something like, and plus heat generated because of endothermicity or exothermicity, plus there may be some kind of cooling coil or heating coil. So, heat is supplied from the outside. So, all these terms may come there, and ultimately if you write your heat balance equation, which you must have learned before. So, heat in minus heat out, right, minus heat disappeared because of chemical reaction or plus heat generated because of the chemical reaction, right. So, that will be the term, right, and if there is some heat added plus Q, if I write, right, that is equal to 0 if there is no accumulation of heat within the system. So, your U g P g times C P g dt by dz is sigma of all these heats because of chemical reaction, right, for all reactions plus U times T minus T A. So, this is a simple energy balance which you must have learned during the your other courses, heat balance, heat transfer courses. So, you can very easily write the balance, energy balance, and one can find out the temperature profile from this equation, because the basic idea is that when you have a exothermic reaction or endothermic reaction. So, for exothermic reaction the heat will generate during the system. So, how much heat is to be removed from the system in order to maintain the reactor at isothermal condition, right, that is important, right. So, that is to be calculated. So, you need to provide a jacket along with some cooling device or cooling arrangement, right. So, you need to find out, or you need to check what is the temperature profile, right. So, whether it is isothermal operation or adiabatic operation. So, what will happen in the system when the heat is generated or heat is being released, right, from the system or not. So, you need to check that, or simultaneously the endothermic temperature will drop. If you do not provide heat, then it will keep on dropping, right, the performance will be affected. One needs to check that. So, in general, if you look at your reactor design, a 3-phase gas liquid, right, catalytic reactor design, which is a multi-phase reactor, right. So, whether it is trickle bed, fixed upflow, bubble flow, right, slurry, 3-phase, right, fluidized bed I will take separately, just some basics of that, right. So, but in general if you look at, the expressions will remain same. So, this is your dispersion term. So, here it is written axial dispersion term, right. So, this is the axial dispersion, right, mass transfer. This is your convective mass transfer term, which we already discussed. This is your chemical reaction term, this will be 0. So, basically input minus output minus this difference because of chemical reaction is equal to 0, and we are assuming that liquid is not transferring into the gas, right. So, this is mass transfer of a gas from the liquid, that is bulk liquid, and to the surface of the solid, right. So, basically it is from bulk to the surface of the solid, and if it is volatile, then you have to just contribute that what is the loss of liquid into the vapor phase. So, you will have some additional term which is here written in terms of the Henry law constant, right. So, when the liquid is partially transferring into the gas phase, right. So, what that is the liquid transfer. So far we are not considering that, right. So, D again the same term, this is again the same term, right, convective, and this is what reported is because of the transfer of the material from liquid. So, liquid phase mass transfer coefficient, right, and this is transferring into the gas, right, and times whatever the P A minus P A I, or in terms of the concentration Henry law, right. So, C G I minus C L, and same thing for the this term is common here again, right. So, I stop here and I will just continue it in my next lecture. So, thank you for today.